Welcome to Learning with Philemon. In the video Oxidation of Alcohols, we saw that primary alcohols can be oxidized to aldehydes and carboxylic acids, and secondary alcohols can be oxidized to ketones using oxidizing agents such as potassium dichromate VI, K2Cr2O7, or potassium manganate VII, KMnO4. In organic chemistry, oxidation can be defined as when a carbon atom gains more bonds to oxygen atoms. In this video, we will be looking at the reverse process, reduction. This can be defined as carbon losing bonds to oxygen atoms or gaining bonds to hydrogen atoms. In the following slides, we will look at different examples of reduction. Carboxylic acids can be reduced using the reducing agent lithium aluminium hydride, LiAlH4. At IB and A-level chemistry, you are not expected to know the mechanism behind this reaction. You are only expected to write an equation showing the process. In this example, ethanoic acid, CH3COOH, is being reduced to ethanol, CH3CH2OH, with water as a byproduct. The H in brackets in the equation represents the hydrogen atoms given by the reducing agent. In the oxidation process, it was possible to use distillation to oxidize an alcohol to an aldehyde and stop there. When reducing a carboxylic acid, you cannot stop at the aldehyde. Lithium aluminium hydride reacts rapidly with the aldehyde, forming the alcohol. Note that lithium aluminium hydride reacts violently with water, so the solvent used cannot contain any water. As can be seen, the carbon in carboxylic acid has 3 bonds to oxygen atoms, a double and a single bond. In the product, the same carbon only has 1 bond to an oxygen atom. The carbon has lost bonds to oxygen atoms and therefore has been reduced. The carbon also goes from having no bonds to hydrogen atoms to having 2 bonds to hydrogen atoms. This is another way to define reduction, a carbon atom gaining bonds to hydrogen atoms. Now let's see how ketones and aldehydes are reduced. Ketones and aldehydes can be reduced using either lithium aluminium hydride or sodium borohydride, NaBH4. In the following examples, we see propanone being reduced to propan-2-ol and methanol being reduced to methanol. Note that in this case, only 2 hydrogen atoms are added to the compounds and there is no water formed as a byproduct. It is often preferred to use sodium borohydride as the reducing agent of ketones and aldehydes, as it does not react violently with water. For this reason, it is safer to use, and the reaction can occur even if water is present. In our final reaction, we will see how nitrobenzene is reduced. Nitrobenzene is formed by reacting benzene with concentrated nitric and sulfuric acid. For more on the mechanism, please watch the previous video, Electrophilic Substitution. To convert nitrobenzene to phenylamine, 2 steps are required. In the first step, nitrobenzene is heated under reflux in a mixture of tin and concentrated hydrochloric acid. The tin is oxidized to form tin II and tin IV ions. Another way to define oxidation is the loss of electrons. In this equation, Sn, tin, is losing 2 electrons to form the Sn2+ ion. This ion can lose 2 more electrons to form the Sn4+ ion. The electrons produced from the oxidation of tin are used to reduce nitrobenzene. Note that reduction can also be defined as the gain of electrons. In the equation below, we can see that nitrobenzene gains electrons produced from tin and reacts with protons, H+ ions, from the hydrochloric acid. The phenylammonium ion is formed and water as a byproduct. For more on oxidation and reduction, in terms of electron loss and gain, please watch the videos in the redox processes playlist. In the second step, the phenylammonium ion is reacted with sodium hydroxide. The hydroxide ions, OH-, remove a proton from the NH3+ group. Phenylamine is formed, along with water as a byproduct. Thank you for listening. To consolidate your learning, try answering the questions in the description. If you haven't already, please subscribe for more content. Stay curious.